Welcome again to this next tutorial in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we had talked about training a simple decision tree classifier to predict whether a material is a metal or not. We will continue our journey today and discuss what happens when you try to train more complex models like a random forest, a simple gradient boosting model, XGBoost, LightGBM and CatBoost. So let us go ahead and get started. So we will start with random forest classification, which is a bagging technique, and you know that random forest is an ensemble method which combines multiple decision trees using bootstrap aggregation, which is short for bagging, and each tree is trained on a random subset of data as well as features. So the random data comes from the bagging part, and the random features it comes from the construction of the random forest if you look back through your notes. So this reduces both the variance as well as overfitting, and random forests are fast, easy to use and robust to noisy data. Okay, so how does all of this work? There is also this website where you can learn more about decision trees and random forests. So you can import the random forest classifier from scikit-learn, and then these are some of the hyperparameters, number of estimators, and the random state of course, which we have discussed multiple times is also very important to specify for ensuring reproducibility of your machine learning models. So this is how we are getting the predictions once you have the model that has been fit through this .fit command. So rfclf is a random forest classifier object. When you do the fit function on that object, the model gets trained, and then you can make predictions based on the predict function on the object, and then you can also predict the probabilities which is essential for making some of these predictions, right. So this is how you can get the accuracy score through this rfclf score. So the score function on the object, then you can get the F1 score, and you can get the ROC AUC as well, the receiver operating characteristic AUC, area under the curve. So this is the classification report that I got. You can see that the random forest accuracy went up from 83 to 91%, that is really nice, and correspondingly the F1 score also improved to 0.91 and the ROC AUC improved to 0.97. So these are all nice things that going from a simple decision tree to a random forest, you can already see that the model is performing so much better. These 4 numbers, if you remembered, some of these entries were actually not that great here, 0.78 and 0.75 for the precision and recall for non-metal and metal, but that has actually increased to 0.91 and 0.90. So this means that the random forest is doing really well on this particular data set. Okay, so now that we have examined how the random forest model is doing, we will go on to gradient boosting, and just as a reminder, we are not going to cover adaptive boosting here. That is a different type of boosting wherein you change the weights of the wrongly classified points in future trees. In gradient boosting, every future tree is going to correct the errors made by the previous trees using the gradient of the loss function which is related to the residual. So gradient boosting builds trees sequentially where each tree learns from the residual errors of the previous one, and unlike bagging, it focuses on reducing bias and can achieve the higher accuracy, but it is prone to more overfitting if we do not tune it that well. Okay, so this is a simple schematic on bagging versus boosting. You know that in bagging, right, you have various data sets, and in parallel you are making predictions, right, from each decision tree, but in boosting you feed the data through one tree, then the next tree will correct the errors made by it, and then the third tree will correct the errors made by the second tree, and finally you will then have an ensemble prediction from all of those. Okay, so let us go ahead and train this simple gradient boosting classifier in scikit-learn. In the lecture I actually told you what is the difference between the scikit-learn gradient boosting classifier and the XGBoost and LightGBM libraries, right. So XGBoost, LightGBM, they are also gradient boosting, but they have a number of very specific features that have been implemented, like exclusive feature bundling or using histograms to partition the splits, right, of the decision tree. So those are really nice thoughtful, carefully determined features that people have introduced into XGBoost, LightGBM and CatBoost. So you will see that those models perform much better than the vanilla gradient boosting classifier that is available in scikit-learn, right. So again, these are the kind of hyperparameters that you need: the number of estimators, learning rate, as well as the random state. And I encourage you to open the Jupyter notebook that you can download from the link and then use that as well. Okay. So by now these parts of the code should be familiar to you. We are again computing the accuracy, we are computing the probabilities as well as the predictions on the test set, and then things like the F1 score, ROC, AUC and the accuracy. Okay. So now you see that the performance of this particular model is actually slightly worse than random forest, right. So random forest, these numbers are 0.91, 0.90 and here they are 0.90 and 0.89. So it is slightly worse than random forest and that is something we will discuss when we tabulate the performance of all the machine learning models. So with this, let us go ahead to XGBoost classifier. You already know that XGBoost is an optimized and a regularized version of gradient boosting, all the advantages we have discussed in the class, and it supports tree pruning, missing value handling and is highly efficient with large data sets. So from this XGBoost library, which by the way you have to install in using the pip install command, you have to then import the XGBoost classifier and you can train the model. Then we have used the log loss as the loss function here. You know that this log loss or binary cross entropy loss is what is used to train a binary classification model, right. And then the other parts of the code are really similar. You get the accuracy, you get the F1 and the ROC, AUC. So I will not spend much time into these because you have already seen these parts of the code before. But I encourage you to look into the syntax of all these functions, because what goes in as input determines what output you will get. So we have to be a bit careful while using these functions here. So now you can see that XGBoost is somewhat similar to your random forest, but it's not as good. But of course the F1 score 0.91 on and the ROC AUC 0.97, they are quite good, if not as comparable to your random forest. And finally we come to the light gradient boosting machine, LightGBM, which is developed by Microsoft. This is a fast gradient boosting framework that uses histogram based learning, and it is optimized for performance on large data sets and it handles categorical features natively. So it does do that, but of course CatBoost also handles categorical features and does much more. So we will check CatBoost as well. Now one major difference between XGBoost and LightGBM is that when growing the trees, when you are making each tree, LightGBM uses leaf-wise tree growth, but XGBoost, when growing the trees, it grows them one level at a time. So that is level wise tree growth. Now due to the use of leaf-wise tree growth, LightGBM can lead to faster convergence and better accuracy, but there is a slight risk of overfitting here because you are not growing the tree across the board, you are growing it leaf by leaf, which is of course the standard procedure even with your CARTs, classification and regression trees. Okay. So from the LightGBM library, again you have to install this using pip install. We are importing the LGBM classifier. You should note that corresponding to each of these libraries there is a LGBM regressor, there is an XGBoost regressor, there is a CatBoost regressor, there is gradient boosting regressor, right. So all the models that we have discussed come with both their classification and regression variants. So if you want to predict regression, if you want to predict a continuous variable in a regression problem, then it is possible to adapt the code that we are discussing here and make it amenable to your problem in a core engineering discipline. But for today's sake we are just going to cover a classification problem. So we are just importing the classifiers and not the regressors. Alright, so we are fitting this LightGBM classifier, and then again the standard part of the code wherein we are looking at the ROC AUC, the F1 score and the overall accuracy. And like I had mentioned a while ago, you can also look at the balanced accuracy score, which in this particular case there is not much imbalance in the classes. So it will be quite close to the accuracy score. So now LightGBM you can see is also very close to XGBoost and not as good as random forest for this particular data set. And finally we come to the CatBoost classifier, and again to briefly remind you, CatBoost is a gradient boosting library developed by Yandex that handles categorical variables natively without pre-processing. It is robust, fast to train and performs well with minimal tuning, and it uses something known as ordered boosting, right, wherein you work with only those features that you need to do the boosting, and this is something that you can read about. The other parts of the code are similar. You have to install CatBoost through pip install, then you have to import the CatBoost classifier, and then again through this you have to define the object, right. We are first defining the object, then using the fit function of the object and the train data you can fit the model, and then you can get the classifier score from the score function on this cat CLF object with the test data, and you can predict the actual classes, you can predict the probabilities which are required when you want the ROC AUC score, right, because it is the area under the curve. So you need the actual probabilities, not just the class predictions there. If you go back to your notes you will understand. Fine. So this is the accuracy for CatBoost, and then these numbers also is very close to your random forest, but not exactly the same. But the F1 score is around 0.91, ROC AUC is 0.97. These are by themselves really excellent metrics. So any of these models you will not go wrong if you use them. And by the way, we have so far not done hyperparameter tuning on these hyperparameters. We are just using whatever hyperparameters that we have, and that is something that we will cover in this tutorial, how to tune the hyperparameters to get even better performance from some of these models. So finally let us compare some of the model performance. You can see here F1 score is 0.90 and ROC AUC is 0.972 for CatBoost, right. So I just copied over all these values into this neat little table here, and from here you will see that apart from decision tree, the vanilla decision tree which is having certain problems, accuracy is low, F1 score is low, ROC AUC is not that impressive, all the other models are actually quite good. I mean I would say that they are almost comparable. Of course if you just want to look at raw metrics, it looks like random forest is better. Of course after you do hyperparameter tuning, it is possible that one of the other models outshines the random forest. So this is the result obtained on this particular random state that we have chosen 42, and the hyperparameter that we have chosen. If you change the random state, or if you do hyperparameter tuning through grid search cross validation, it is possible that one of these other models will outshine, but I leave that to you as an exercise. So this is where you have to actually do some of your own work at your own end. You have to train these models, do hyperparameter tuning, and then try to develop a feel for which one is better for which particular data set. So these are the overall takeaways. The random forest model is the best overall performer, and it offers a pretty good highest F1 score of 0.9128, indicating the best balance between precision and recall. It has the highest ROC AUC of 0.97, which demonstrates a strong ability to distinguish between the metallic and non-metallic classes. And LightGBM, XGBoost, even CatBoost, these perform nearly as well and are excellent alternatives. Alright, so one final comment, decision tree shows a lower performance across all the metrics, making it less ideal for production use unless you really value the model simplicity or interpretability, right. By the way, there is a way to actually plot the decision tree and then see how the splits are happening. So I encourage you to do that at your end. That will give you a feel for how the decision tree is working through the data points, and thus the model is interpretable. But again, this is left to you as an exercise, because otherwise the tutorial will become too long. Alright, the next thing that we are going to cover today is feature importance analysis with this Shapley additive explanations, the SHAP method for the random forest model. And why we are into feature importance analysis? Because it helps us understand that which input features contribute the most to a model's predictions. and traditional feature importance methods like Guinea importance in random forests can be less interpretable, but the good thing about the Shapley method is it is additive, right. So, you can add the importance of features and then you know together how much they are important, and it is able to do this because it is based on a concept in cooperative game theory. You can read the original paper, and this SHAP method assigns each feature an importance value for a particular prediction, and not only that, it tells you whether high values of a feature are correlated with a high target variable value, and if vice versa, and if low values of a feature are correlated to a low value of the target variable and vice versa. Now, the SHAP method is particularly consistent. If a model relies more on a feature, SHAP assigns it higher importance, and it is interpretable because it also explains, like I just said, whether each feature pushes the prediction higher or lower. Now, we will use SHAP to visualize which chemical features most influence the model's classification of a compound as a metal or a non-metal, and for more details on SHAP you can look at the official documentation which is available at this particular link, github.com/SHAP/SHAP, and then there is also the documentation for SHAP which is available, and from the notebook that we will share, these links also will be there and you can click and access them. Alright. So, we have just imported the SHAP module here, again it has to be installed, and then through this tree explainer function we are just passing the random forest classifier object. So, this object, right, as you know that we are now in the era of object oriented programming, OOP, and we work with objects and functions. So, this is the RFCLF object which has been fed into the tree explainer function of the SHAP library, and then from this explainer object. So, this has returned to you the explainer object, and then this explainer object has been passed to the SHAP values function, and then you can actually do this summary plot function again available in SHAP, and pass not only the SHAP values but also the test data set, the feature names, and so on and so forth. So, let us see what we get when we do this. So, this is the plot of the SHAP importance analysis, and you can see that there is a color coded bar here. So, low is blue and then high is red, as is usual in any legend, and you can see that the features which are most important are at the top, and then you list the features of lower and lower importance as you go down this particular column. Okay. So, the most important features is the mean number of valence electrons, and you can see that low values, right, low is blue, low values of the NP valence, they contribute positively to the prediction of whether it is metallic or not. So, you can see that this is the dividing line, and this is the SHAP value which is impact on the model output. So, if your valence, right, NP valence feature is low because blue color is low, then it makes the metal more the material more metallic, right. On the other hand, if you look at a feature like the maximum Mendeleev number, if you focus on this high feature value, because red is high feature value is correlated with a negative SHAP value, meaning it makes it more non-metallic. And similarly, you can see that low column value is related to it being metallic. We already discussed this, by the way, in the Seaborn analysis, wherein you saw a correlation, and a high value of the column is related with a negative impact, and negative impact in this case means class 1, and so you can see how you can interpret this kind of an analysis. It is really nice. You can make out what these kind of features mean. You have the maximum NP valence, maximum column, melting temperature, band gap, and so on and so forth. Alright. So, this concludes our discussion of the feature importance analysis, the SHAP feature importance. Later in this tutorial we will also discuss the permutation feature importance analysis. There are various other feature importance analysis method, the Borota feature importance analysis. I would encourage you to go and read about these feature importance analysis methods. There is not much time to cover in this course how they work, but nevertheless an understanding of these is very important, because you, at the end of the day, you want to interpret these models, which feature is less important, which feature is more important. That will give you some insight into the physics or the chemistry or the biology of the problem. Okay, so now we switch gears and we move on to the concept of hyperparameter tuning, and this we will do with a grid search approach. And if you recall, hyperparameter tuning helps us find the best combination of parameters to improve accuracy, generalization and robustness of the model, and we will use grid search cross validation, which systematically searches through combinations of parameters to find the best combination that we should use, right. And we will pick the random forest model to tune the hyperparameters. These have several important ones like the number of trees, the depth of the trees and so on, which can significantly affect the model performance. And by default, like I had mentioned slightly earlier, these parameters are not optimized, which can lead to suboptimal results. Okay. So what we are doing here is from scikit-learn.ensemble we are importing the random forest classifier, and we are also from sklearn.model selection importing the grid search CV module. Okay. Now before we do grid search cross validation, of course we have to define the grid of parameters that we are using. So we are giving this grid based on our experience, based on our understanding. Of course one can expand this grid to have many more possible choices of the hyperparameter values, but this has a multiplicative effect on the number of models that have to be trained, right. So here we are giving 2 values of the number of estimators, 3 values of the max depth, then 2 values of the minimum number of samples when you split, and then 2 values for the minimum number of samples in a leaf, and then 2 values for whether bootstrapping is allowed or not, right. So the total number of models that will have to be trained for this grid that we have specified is 2 times 3 6 times 2 that is 12 times 2 that is 24 and times 2 that is 48, right. So 6 times 2 times 2 times 2, that is 48 models have to be trained. So you can now understand, if I make any of these hyperparameters have one more possible value, then it is going to blow up, right. So slowly and slowly the number of models that have to be trained will keep on increasing. So it is very important to choose these values here for the grid carefully, and then of course if you have the compute you can train more models, and that is fine, but this is the number of models trained in total. Alright. So again we have to have a base model, we are initializing the model, then we set up the grid search CV function wherein we have to tell what is the estimator, what is the parameter grid. So parameter grid was defined here, how many folds we have. So here we are doing 5 fold cross validation, so CV value is 5. What is the metric that is used for scoring? We are using F1, so we will compute the average F1 score over all the folds and so on and so forth. Okay. So we are now using the grid search object, which was defined using the grid search function, and on this object we are doing the fit function with the training data, and then at the end of this exercise it will print out the best set of parameters through this particular variable here, grid search dot best params, and the best estimator can also be obtained. Alright, so the best estimator will be the best value of the F1 score, because we are using the F1 score for scoring, as can be seen here. Alright, so now we are evaluating again on the test data, and you can do all the analysis after hyperparameter tuning on the test data. You can actually evaluate the best model, right. So the best model you can use to make the prediction. So, the best RF was the estimator that you got, and then from that you are making predictions of the test data, you are getting the probabilities which are required for the ROC AUC score, and then this is simply the basic accuracy score on the best model that also you will get. Right. So, after hyperparameter tuning you are getting the F1 score, the AUC, as well as this classification report which has all the required values. So, let us see how the output looks like. The output of course is a bit long here. So, the code tells you that it is doing a 5-fold cross validation for each of 48 candidates. Okay. So, we did this calculation here how there are 48 model candidates. So, that was 2 times 3 times 2 times 2 times 2, that is 48, and that totals 240 fits, because each of these candidate models has to be tuned 5 times, because we are doing 5-fold cross validation. So, that is already 240 fits, and you will see that this particular exercise takes a bit of time on your computer. Now, if you increase this to 10-fold cross validation, then you are talking about 480 fits and so on and so forth. At the end of the exercise it will tell you what are the best parameters, right. So, bootstrapping is not recommended for after cross validation. Max depth we want 20. So, the values we had given were 10 or 20. So, it selected 20 as the best choice. The minimum samples per leaf, it is saying that we choose 2 rather than 5. Minimum samples leaf, it is saying 2, right. Minimum sample split is also 2, and the optimal number of estimators is 200. And after hyperparameter tuning, the accuracy score is 0.92, the F1 score and the ROC score have improved. Okay. So, this is the classification report, and if you compare the metrics after tuning, it became 9191 and the ROC AUC increased slightly. So, the takeaway is that the hyperparameter tuning slightly improved the performance of F1 and ROC AUC, suggesting that the model generalizes better and classifies unseen metal non-metal samples with higher precision and recall after this exercise has been completed. Alright. So, of course, you can print also what is happening in each fold, right. That will be seen, but I am not showing it here for the sake of brevity, but you are free to see exactly, right, in every fold what performance was given by each of these 48 candidates. Of course, there will be a lot of pages of information, but you are welcome to analyze and understand that. Okay. So, with this we have completed our discussion of the tree based models. So, that means we have covered XGBoost, LightGBM, CatBoost, we have also covered the simple decision tree as well as the vanilla gradient boosting which is available in scikit-learn. So, now we change gears, we are going to move on to the topic of support vector machines, and we will understand how that can be used to train a classifier. So, let us go ahead and get started with this, and first do a recap before we show you the coding. So, support vector machines are powerful models and they follow a different approach, right, compared to kernel based methods like SVM. So, what is SVM? SVM is a supervised learning algorithm which can be used for both classification and regression problems, and these work by finding the optimal hyperplane that best separates data points from different classes in a high dimensional feature space. And we discussed what is meant by a hyperplane is the extension of a concept of a line in 2D to a plane in p dimensions if you have p features, and this hyperplane concept can be also used for classification, because in each region of the feature space you have a hyperplane which can tell you how the target variable depends on the feature in that part of the feature space. And the goal for classification support vector classifiers is to maximize the margin between the classes, which is the distance between the nearest data points, that is the support vectors, and the decision boundary. If you go back and look at your notes, all this will become very clear. So, this is an illustration which is derived from this particular website here. You can see that yeah, you have two classes here, we are looking at binary classification here. This is class 2, this is class 1, and we have a decision boundary here, and then these are the two support vectors. The closest points they lie on the support vectors, and then we are trying to maximize the distance between the support vectors, right, that is the margin here. Okay. So, a question arises, why should we use support vector machines? So, the answer to that is support vector machines are especially effective in high dimensional spaces, and they perform well when there is a clear margin of separation between classes, and as we have studied in the theory lectures, they can handle nonlinear classification problems as well using the so called kernel trick. So, if you have a radial basis function kernel, RBF kernel, you have a polynomial kernel, Mattern kernel, and so on and so forth, and these can bring in nonlinearity into the problem. So, now that we have seen how the tree based models are performing on our MathBench ISMATL data set, let us explore how the SVM model fares on our classification task, right. So, now comes the distinction from decision trees. We had already discussed that no scaling is required when using decision trees, because they are just splitting the data set into various regions, whereas with SVM or with other models like linear regression, logistic regression, neural networks, scaling standard scaling can help a lot, right. So, first we are going to do a without scaling SVM, then we are going to do a with scaling SVM. So, we are doing the classification task. So, from sklearn.svm we are importing the support vector classifier, and then of course the metrics like the classification report, F1 score, ROC, AUC score, all of these are by now standard. Now we are training the SVM model with this radial basis function RBF kernel. This is a classifier, this is the random state, and so on. And after the model is fit through this dot fit function on the support vector machine object, then you can use this object to make predictions of the test data, and you can also predict the probabilities, right. And finally then you can have a classification report here, right. So, this part of the code is very similar to what we had previously. So, now you can see that this particular model performs even worse than the vanilla decision tree that we had. The accuracy is quite bad, F1 score, ROC, AOC, none of them are very high. This is the confusion matrix, if you remember in class, and we could have done this even for the decision trees. So, I encourage you to explore the concept of a confusion matrix, but this is essentially telling you how many of the points were correctly classified as non-metal and how many of them were correctly classified as metal. So, those are the diagonal entries. The off diagonal entries are the incorrect predictions. So, this is a non-metal being predicted as a metal, and this is a metal being predicted as a non-metal. Of course, they will affect the true positive and the true negative rate. Okay, so now that we have covered the confusion matrix, we can go ahead and look at support vector machines with scaling. So, to do this we are going to import the standard scaler from sklearn.preprocessing. Alright, so first what we do is we scale the features by using the standard scaler on the training data, right. So, to prevent data leakage, it is important that the scaler is only applied on the trained data, and once the scaler is decided, right, by how much you have to shift each variable to make the mean 0 and by how much you have to scale them to make the standard deviation 1, once those quantities are decided by the fixed transform method and stored here in this scalar object, then you can apply the same transformation to the test data, and in this case, in this way you are preventing data leakage by determining the scaling factors and the shifting factors only based on the training data and then applying it on the test data. So, now we can train an SVM model with the scaled features. The code remains the same. Using the SVC function, you are creating an object with the RBF kernel and the random state specified, and then once the model is fit using the fit command, you can then go back and make the predictions as before, and you can look at a confusion matrix as well. So, this is the code to obtain the confusion matrix. You have to specify the predicted and the test y values. alright, and this heat map function from Seaborn is actually used to make the confusion matrix. So now you can see the accuracy, F1, ROC, AOC have gone considerably up after you did scaling. So this tutorial tells you the importance of standard scaling for models such as SVM, which was not required in decision trees. So this is the new confusion matrix. You can see that the number of entries on the diagonals which reflect the correct predictions of the model have gone up, right, 659 and 647. Here there were only 573 and 581, and the number of predictions on the off diagonal, which is the wrong predictions, 168 and 155, they have actually come down to only 82 and 89. So standard scaling has helped so much when developing a support vector classifier, and this is something that you should retain when you try to apply these kind of models in various core engineering disciplines. Okay, so now let us compare the SVM performance before and after the scaling. So what we already saw was that feature scaling improves the performance of the SVM model. After applying standard scaling, all the metrics, the accuracy, F1 score, ROC, AUC, they showed substantial improvement, right. So these were before scaling numbers, and these are the numbers after scaling. So all of them have gone up. So the takeaway is that SVMs are sensitive to the scale of the input features. So apply feature scaling like a standard scaler or other scalars also you can try before training an SVM, and always remember to first determine the scaling and the shifting quantities on the trained data and then apply it to the test data to prevent data leakage. Okay. So now to evaluate the classifier's ability to distinguish between metallic and non-metallic materials, we can also plot the ROC curve and then look at the AOC. So the ROC curve illustrates the trade off between the true positive rate and the false positive rate at various threshold probability settings, and the AUC is something we already discussed. It provides a single metric summarizing the model performance, where closer to 1 indicates better model discrimination. Okay. So now we are computing through this ROC curve and the AOC function available in sklearn.metrics. We are computing the false positive rate, the true positive rate, the thresholds through this ROC curve applied on the test data and the test predicted probabilities, and then this AOC function based on the false positive rate and the true positive rate will give you the ROC AOC. Alright. So once that is done, you can plot the ROC curve, right. That is just a plot of the true positive rate versus the false positive rate, and then of course the range is between 0 and 1, and you can also stylize the axis in the text to make the plots look good. This is of course required whenever you are making any presentations or reports. So this is the ROC curve for the SVM classifier. I already told you in the lectures that this is the 45-degree line in the TPR versus FPR plot is for a random classifier, something which will just randomly tell you whether it is class 1 or class 2, metallic or non-metallic, but our model of course does much better. It follows this orange curve, and if you had plotted the ROC AUC curve for one of the superior models, right, like the random forest or the XGBoost, this curve would have shifted even above. So I encourage you to go back when we develop the random forest model, we develop the XGBoost, LightGBM, CatBoost models, you can make the ROC curve receiver operating characteristic curve even for those models, and this is left as an exercise for you to do. So we had only looked at the AOC there, but you can look at the ROC as well. Okay, so what can be done next is you can actually tune the hyperparameters as well for the support vector machines, and these are some of the key support vector machine hyperparameters. As you remember, there is a regularization parameter in support vector machines which controls the trade off between achieving a low training error and a low testing error. Smaller C values keep the decision surface simple but lead to a higher training error. Larger C values, they penalize making errors more, and thus it tries to does it tries to fit the data better. Then the kernel that you are using, linear, radial basis function, polynomial, this is also a hyperparameter, and then this gamma is a parameter that appears in all kernels. It scales the dot product, right. If you remember, in kernels you have to take the dot product of the ith feature vector and the jth feature vector, and typically this is scaled by some gamma as it goes into the kernel. So whether it is a linear or a polynomial kernel, there is always a scaling factor for this dot product. So this scaling factor determines how far the influence of a single training example, right, say point xi reaches, and high gamma leads to overfitting risk and low gamma leads to a more generalized model. And in this case we will use randomized search CV, just to show you that instead of grid search CV you could also do randomized search CV, and randomized search CV is a powerful technique for hyperparameter optimization that samples a fixed number of parameter combinations from a specified distribution, is faster than grid search CV when the search space is large, because you do not have to look at every possible combination of the hyperparameter, and it helps you avoid overfitting by exploring a broader space with fewer evaluations. So instead of exhaustively testing all possible combinations, as in grid search, we select a random subset of combinations and evaluate them using CV, and this makes it ideal for expensive models like support vector machine, where a lot of optimization is going on behind the scenes to formulate the best hyperplane. So SVMs can be sensitive to hyperparameters, especially when using nonlinear kernels like radial basis functions, and a proper tuning of the C, gamma and the kernel helps improve the model performance on unseen data, reduce overfitting and find the best decision boundary for complex data sets, right. So the takeaway is for SVM that always scale your data and perform hyperparameter tuning when using SVMs for optimal performance. Okay. So this is the space where we are importing the randomized search CV from sklearn.model selection. We are also importing, of course, the support vector classifier and the uniform distribution from scipy.stats, because that is the distribution we will be using in randomized search CV, right. So we are specifying the C parameter as a uniform distribution between 0.1 to 10, the gamma value as a uniform distribution between 0.001 to 1, and the kernel as one of 3 random choices between RBF, poly and sigmoid kernels. Okay. So first we have to initialize the support vector classifier, we are trying to predict the probability and the random state, and then this is where we set up the randomized search CV. This is being applied on this SVM object, that is the object name we have given here, the same object name should appear here. The parameter distributions have been specified, we have used the the uniform distribution here. You can also use a normal distribution, you can use exponential distribution, whatever kind of distribution that you want. This is important, that is the number of parameter settings to try. So it will sample randomly 20 points out of this parameter distribution and then use that to do the hyperparameter tuning. The scoring will be done with the F1 score, there are 5 folds that are being used, and then this is the setting for verbosity, how much output you want to see. I am setting the verbosity at 2 here and the random state is 42, and you also have a parallelization setting. Okay, so now we are running the search on this scale data, right, to predict the train values. Then you can find out the best SVM model, right, this is the best model, and you can also print out the best parameters. All of these are stored in this object here, random search object, which we had initialized by the randomized search CV function, and we had even fit this object, and that is how we know that the cross validation was done. So once the best estimator is found, you can make the predictions on the test data. You can also have this classification report wherein you look not just at the accuracy but again at the F1 score as well as the ROC AUC score. Alright, so this is this time I am showing you exactly how the output looks. I have not deleted the output like I did last time. So this is fitting 5 folds for each of 20 candidates, totaling 100 fits. If you remember in the earlier case there were 5 folds and then there were about 48 different choices of hyperparameters, so there were 240 fits. So with random search CV you can use a fewer number of fits, and what it is telling you is these are the randomly chosen parameters that is using. C is this particular randomly chosen number from the uniform distribution, gamma is this particular number from the uniform distribution, and kernel is sigmoid, again chosen randomly. It took 3 seconds to train this folds. So, these are the 5 folds, fold 1, fold 2, fold 3, fold 4 and fold 5 with these parameters, right. So, you can see that within these folds the parameters do not change, and then of course, you will have an entire set of 20 different parameters. Alright, so that is a long output. So, you can see that at the end of this exercise it will tell you what are the best set of parameters. I encourage you to go through the Jupyter notebook, which we will upload on the NPTEL website, and you can scroll through very carefully through all of these folds and all of the random choices of the parameters that were made. So, finally, at the end of the scaling and the hyperparameter tuning, what we have made sure is that these performance metrics are somewhat close to the random forest classifier that we had developed so easily without doing all this hard work, right. So, you can see how models like random forests and gradient boosting have really come about and overpowered more classical models like support vector machines, but of course, even with SVM with all the effort like hyperparameter tuning you can get better performance. Okay. So, in summary, feature scaling had a significant impact on the SVM performance. After applying the standard scaler, the metrics such as the accuracy, F1 score and ROC improved dramatically, and further tuning the model using the randomized search CV helped push the performance even higher by finding the optimal parameters for the regularization parameter, the gamma and the kernel that was used. So, this is before scaling. You can see these metrics are really low. Scaling did push them up, and the final push we got through hyperparameter tuning as well. So, the takeaway is that feature scaling is extremely crucial for SVM type of models. The hyperparameter tuning further refines the decision boundary, leading to a better classification performance, and a combination of pre-processing and model optimization unlocks the full potential of support vector machines. So, this brings me to the end of this particular tutorial. This was a slightly longer tutorial wherein we took the time to look at not only hyperparameter optimization of the tree based models like the random forest and how that helped us improve the performance. We also had a more closer look at things like a confusion matrix in a classification model. We looked at the receiver operating characteristic ROC curve, we looked at the area under the curve, then we switched gears and went to support vector machines, wherein we discussed that you have to use a standard scaler or other appropriate scalars, and you also have to do hyperparameter tuning to get the performance of these more classical models up to the modern models like gradient boosting. So, I hope you learned something new. In the next tutorial we will continue our discussion of the Gaussian process regression framework. Thank you for joining and see you next time.